Good morning and welcome to our FPGA event. It's the first one that we have been holding in Cambridge, but there is a plan to come back each year, one event each year, and I'll give more details on that. Okay. So all the presentations, slides and recordings for today will be available after the event, and you'll get an email about that. If you've got any ideas, or if you want to make a presentation on the FPGA, then you can contact me or tell me today. I've already picked up some contact details for one company you want to present. Okay, and this is the plan for next year. We hold one a quarter. The first one will be in Vanishaw again. We had a very good event there during 2024, and that's about using AI in development of products of FPGAs. Okay. This year we held our verification strategies, and that was held in Rolls-Royce. But next year it's going to become a stream within our verification future event, and that's held in Reading, and that's alongside the ASIC. And so there'll be a lot of other people there as well. But it's going to be a stream within verification futures. The technology roadmaps will be in Cambridge again, but rather than safety and security, which is what we've got today, but will become technology roadmaps. And safety and security will move back to TARES in Reading. Okay, so that's the plan for next year. There's a little blip with TARES today, and it's about getting the right context so we can get our venue. But we'll be back there next year. Thank you to our sponsors, and a big thank you to Synopsys and Sundance. Thank you very much to them for sponsoring today. And of course, TechWorks who run the event, and the test on with my employer, and allow me to do this. Okay. Right. I think we're going to go straight to our first speaker. Is that okay, Disha?
Yes. Tobias, can you share your screen, please? Yes, perfect. I can see your screen.
Do you want to mute? Do you want to mute me?
Mike, you're able to see the screen?
Yep.
Okay.
Can you mute me? Do you want to?
Mike, you're going to make an introduction for him, or he needs to start?
Okay, so our first speaker today is Tobias Adrian from Synopsys. He's a field application engineer, and he's going to be talking about securing FPGAs beyond the bitstream. He had over 10 years of experience in the field of security and PUF technology, held positions as a hardware engineer, product manager, field application engineer, and he helps customers worldwide reach ever higher levels of security within the needs and constraints of their use cases. He's based in Belgium, and we're going to hand over to him now. Thank you.
Okay, good morning, everyone. So yeah, I'll be talking about securing FPGAs beyond the bitstream. It doesn't mean that we can't help with securing the bitstream, but generally the use cases need more than just the bitstream, and that's what I'll be talking about today. So I'll start with a brief introduction on Synopsys PUF or PUF in general, even, and what you should be looking for in a PUF for an FPGA application, and even a PUF in general. Then I'll talk a little bit about our puff in AMD Xilinx FPGAs, because that is kind of a special case for us. And then I'll dive into a secure key vault use case example. It's one of the simpler use cases that is easy to explain and to talk about. That usually also is the basis of most of the use cases, that even the ones that get more complicated. And I'll of course end with a conclusion. Okay, so bitstream protection is not enough for most applications. Modern applications need more security. So even if the FPGAs you are running on are 15-year-old chip design, you still need security that holds up today. Many instances need more than that is offered with these devices, even the more modern FPGAs. For instance, users need key storage. Sensitive keys should be protected even from the FPGA manufacturer in many use cases. Keys should not or may not even be known at the time of manufacturing, and should not be known by the people handling the manufacturing. And most importantly, even keys should be updatable over the lifetime of the device. So when you have one application or one mission for an FPGA, they might be deployed somewhere else in a different application that need new keys, and that should be updatable. So in general, we have learned all that supply chain cannot be trusted. We've seen various breaches over the years, even with FPGAs, and minimizing exposure of sensitive material in that case is very crucial. So finally, keys and secrets must be unclonable, since we're all using off-the-shelf devices with external flash. Things have become more and more easy to extract from these devices, whether it's keys or the whole design or manipulating design in flight. It has become increasingly easy. Reverse engineering services can even be ordered online now. For some devices, generally not for the FPGAs, but for some devices, less than for less than €1,000. So that is hardly a fair trade for the hard work we all put into the development of our devices and for the secrets that we are putting into these devices to protect the application of them. So to protect data, we need to have strong keys. And first, they need to be unpredictable and unique per device. Ideally, the whole security setup should lean itself towards that. Secondly, keys need to be protected. So when they are in the device, you need to retrieve them some way. And that should be easy for you in the application, but that should be near impossible for an attacker. So unclonable and immutable are the two properties that you should be looking for there. So with PUF, unlike legacy key storage mechanisms like ROM, flash, or fuses, where changes are made to the security to store these secrets, PUF will only generate and regenerate that key when it is needed by the application. So the key disappears when there is no longer a need and leaves no traces for the attacker to reverse engineer them. In a bit more concrete way, legacy applications or legacy key management, at least what we see as legacy key management, often keys are injected from the outside. They need to be generated externally. They need to be handled externally, maybe even by multiple parties in the manufacturing chain, which makes them sensitive to leakage, because if some multiple people have to handle databases with all these secrets in there, there might be a problem along the line. The next step would be the storage of those keys. So they need to be stored somewhere to be able to retrieve them during the application. This is often done with OTP, which also is something, or fuses, which also is something that can be reverse engineered by someone taking a deep look at these devices. Another option would be to use a secure element or an external security chip. But when you end up with a two-chip solution with an interface that is potentially vulnerable, but because that interface needs to be protected from both sides. Both sides need to handle keys, and the very reason why you wanted that secure element is to do that key protection, so that it's kind of a flawed setup from the start. So with PUF technology, the root keys are created from within and never need to leave the security perimeter of the device. So since we have the same key can always be, since we have the same key that can always be re-derived from the PUF fingerprint, it doesn't need to be stored anywhere permanently. It will never be present on the chip when it's not powered. This completely eliminates the classical root key extraction attacks, like delayering the chip and reverse engineering it. Another advantage compared to external root key injection is that no secrets or sensitive keys are ever exposed in the device's supply chain at any point in the life cycle. And of course, some use cases might require that. So there's possibilities to regenerate keys or derive keys that can be used externally, but the root key of the device never leaves the device itself. And with PUF, because you are using this from within, you can do this at any point in the device lifecycle. So you might include the IP from the get-go, but only when you need to deploy them, you provision the secrets that are needed for that deployment. So that way, the PUF IP delivers higher security through that flexibility enables you to lower the cost for that process. I've now talked about PUF for a while. I'm not sure if that is a familiar term for everyone, but it's time to explain what PUF is and what kind of PUF we are using. So we are using the butterfly PUF cell, which is a cell consisting of two cross-coupled memory elements that have a bistable output. So the butterfly PUF can only have two stable possible outputs. However, there are three states shown in the diagram. And the very bottom, the point A, you see a stable operating point that we will call now representing 0. Point B is the unstable operating point, which will become important in later. And C, the top stable operating point, which we'll call representing 1. The cell is evaluated by exciting it. So this is done by bringing it to the unstable point B and then releasing it. Upon release, the device will decide based on the drive strength of these cross-coupled memory cells where to fall to. So it either falls back to A or back to C to either represent a 1 or a 0 for that particular cell. And these cells are then used in an array to make up a device fingerprint to identify it later and reconstruct the keys. So the way this works is it's all based on process variation. So while all of these digital circuits are generally made to be as identical as possible, they never are. The individual transistors will always be slightly different for various process related differences. So each and every one of these cells will have a preferred state that it falls back to. And if you look at that in an array, you get something that we call the silicon fingerprint. The base operation of this, you just have cells that have either a very strong preference, so let's say 90% of the cells have a very strong preference, and they will always respond in the same way. So once they come up as a 1, they will always come up as a 1. Once they come up as a 0, they will always come up as a 0. The remaining 10% will operate in a range. So they might be 99% 1 and 1% 0. They might be 50-50, where every time you excite them, they will come out different. These are the bits that we call noisy. And what our IP does is to convert this noisy silicon fingerprint into a full entropy and, most importantly, stable key for use as a foundation of a security subsystem. And the way that works is in a two-phase process. So we start with the enrollment, which is typically a one-time process. We can do it multiple times in the device lifetime. Some use cases make use of that. but typically it only happens once. And during that enrollment, the butterfly puff is read out by the IP, and the IP generates something that we call the activation code. And that activation code is then subsequently used during the key reconstruction. So during the key reconstruction in the field, we have a new response of the puff. You read it out again. This time it's a little bit noisy compared to the previous one. And together with that activation code, we can always get back to that root key again. There are two very important properties that this activation code gives us. This activation code is entirely non-sensitive. So it can be stored on chip, it can be stored off chip, it can be handled by a master device and only provided upon reconstruction. As long as you have it available when you want to do your key reconstruction, you are good. There is no additional care that needs to be taken to store and retrieve this activation code. Secondly, this activation code allows us to make this extremely reliable. So 1 in a trillion is a typical key reconstruction failure rate. So for this second part of the process to fail, let's say. And even if you would be, let's say, one unlucky customer that ever encounters this, for whatever reason, you can just retry and do it again with the 1 in a trillion chance of this going wrong. So that's not going to happen twice in a row. Then we get to the secure key vault use case. So what I've chosen here to show is a secure key vault use case, and it shows the most fundamental use case. So it is, let's say, quite simple and straightforward to understand, and it is something that lies at the basis typically of most other use cases as well. And this allows secrets to be stored securely on or off chip and protects confidentiality and integrity of the secrets that are stored. And it does this by leveraging the NVM that is in the system. This can either be on or off chip. And it uses these device unique properties to generate a strong, reliable cryptographic key, and then can be used to encrypt and authenticate data or users or even access to the device. So we start with the enrollment. As mentioned before, this process is typically only done once, early in the device lifetime. And we start with the puff IP reading the butterfly puff cells. The puff IP then constructs the internal puff root key and outputs the activation code. That activation code can be stored in the flash, which is typically the external flash, that also holds the bitstream in the case of an FPGA. And at this point, we have set up the system enough to do all the key storage and key operations that are enabled by the IP. And we can go ahead with storing keys. So in this one, I assume, because this often is part of the use case, that the previous step was done elsewhere, and we have to reconstruct the internal puff root key before we can continue. But if this step was performed right after we stopped in the previous slide, we could skip step 1, 2, and 3. However, we are assuming that we are going with a fresh start. So we start again with the IP reading the butterfly puff again and reading in the activation code. This then reconstructs the internal root key and brings us to the same state we were in with the previous slide. In most use cases, our customers like to use the same key on multiple devices instead of using only device unique keys, because it allows for some optimization in the use case. Obviously, it is going to be advantageous if you just use device unique keys. That would even further simplify this use case. But since that is usually what our customers like to do, that is the one that I'm highlighting here. And in that case, the user chosen keys can be encrypted and authenticated using device unique keys, and that is what we call key wrapping. So to wrap that user chosen key, we use the wrap operation, unsurprisingly. Internally, a new wrapping key is derived to wrap that user key, and that wrapped user key can then be stored externally again, like we have done with the activation code before. And as before with the activation code, that wrapped user key, that the binary blob that you get out of that, is insensitive to or is not sensitive information to anyone, so you can store it externally, it can be handled by anyone. It will be authenticated before it is going to be used by the IP. So it's important to state here that we now have a fully provisioned system. Granted, it's a simplistic system, but it is fully enrolled and ready with the secrets that we need for our use case. The highlights here are there is no sensitive data anywhere in the system. So there are no keys stored, or no keys or sensitive data stored in any volatile memory. There are no keys or sensitive data in any fuses, embedded flash, or battery-backed RAM. And there are no keys or sensitive data in external flash. So so there are no keys or sensitive data in any external flash. So the system is entirely inert at rest. So now we go, let's say, to the normal in the field usage. So all of this, these previous slides were the setup to get to where you need to go, and the steps on this slide are what you will typically see in the device usage. So again, the puff reads out the butterfly puff and reads in the activation code, and with that reconstructs an internal root key again. Since the user wants to use its key, we have to use the unwrap operation. So that's the counterpart to the wrap operation. And the wrapped key will then be retrieved from the flash. The wrapping keys will be derived again. The authentication tags will be verified, and the key is decrypted. At this point, depending on how it is configured in the IP, the unwrap operation then will output the key again. This can be either directly to the software controlling this, or can be to a hardware secure interface that goes directly to things like crypto accelerators to avoid any exposure in the software layer. So this kind of flexible key provisioning is unique to our puff products, and it allows provisioning to occur when and where the business needs it. This is simply not possible with key injection or using external secure elements. By having this flexibility, it eases the operational burden, complexity, cost, and liability of the supply chain, not only for parties like the silicon manufacturer or the users, but for everyone in the system, like OEMs, contractors, and everyone that would be involved. So why would you want to use Synopsys for your security IP? We have a broad portfolio of scalable hardware and software security IP solutions. We start from build your own with all the blocks that you could possibly need to build your own specific use case, to fully integrated solutions that enable things like secure authentication of data, key management, platform security, content protection, and so on. Our solutions are silicon proven in a range of applications. For instance, cloud computing, automotive, but also aerospace and government, consumer, IoT and industrial IoT. And we are a world-renowned security team with the industry recognized experts and pioneers in that of technology. Okay, so this was the talk so far. Any questions?
I'm trying to get. Hello.
Brian Downey, European Mission Consultants. What's the purpose of the activation code? Is it required, and what does it add?
So the activation code actually enables us to do all of this in a reliable and secure fashion. Because like I've seen in the chat also a few questions, the cells and the response of these cells will be slightly altered over time or over temperature or voltages. So to make this high reliability and high availability, we have this activation code, which if you look it up in academia, It's mostly called helper data to enable us to deal with any amount of noise that you would expect in the real world.
Thank you.
Thank you. Any more in the room? Other than that, Tobias, do you want to read out the ones in the chat and answer them? Can you see them?
Yes. So I see in the chat there's also a Q&A, I guess.
Yes,
Okay.
yes.
Yeah. Yeah. So as I said with the previous one, the butterfly puff itself will vary a little bit in its response. So that's the noisy bits that we have to deal with, that 10% of bits that might be influenced by external factors like temperature or voltage or time. But those changes are all managed by that activation code and the algorithms that we use internally to be able to correct all of these and return to that key every single time again.
Okay, I think that was it. That was the only one online. We've got some come in via WhatsApp. I think we've got some time. So, can you give some examples of devices where Puff has been deployed?
Oh, okay. Yeah, too many to list all of them, but there are quite a few examples that I can give. So we have a lot of deployment in server applications to secure those high value chips and IP that are dealt with there. For flexibility, IoT devices and industrial IoT devices like us as well, wearables, health, medical, aerospace even. So we have our IP deployed in more than one satellite in space. So yeah, lots of different ones. It's very multi-applicable.
Okay, and do you got some examples of high security environments?
Yeah. So again, also many different ones. So I would say that the most high security environment that we are dealing with is aerospace and government, because they're you're taking care of high risk situations. You are dealing with critical infrastructure, but we also have deployments, quite a lot of them actually, in payment and identity cards, where security is also of the utmost importance, with a wide range of the environmental extremes that you have to deal with. And in those cases, we protect the integrity of the application, but also the protection of the firmware, and so on. So unfortunately, many device manufacturers don't like to broadcast what their security solution is. So we were not, let's say, at liberty to share exactly what everyone is doing and what the exact devices are out there in the field. But there are many. As we know, security is important for everyone and every application in the end. So it's wide.
Okay, that's perfect timing. We're finished there. And we'll give you a round of applause here.
Okay, thank you. I'll stop the share. I'm sure somebody else is itching to go.
Yes, we have a next speaker, Aspen. Aspen, if you could. Thank you, Tobias. If you could share your screen, please. Yeah, thank you. Mike, if you can do the introduction, please. Mike, we are not able to hear you.
Our next speaker is Aspen Talascan from EM Logic. He's the managing director there. He's going to be speaking about FPGA requirements tracking and traceability matrix. Okay, he's based in Norway. He's author and architect of UVVM, which stands for Universal VHDL verification methodology, and that's an open source resource. He has a strong interest in methodology, cultivation, pragmatic efficiency, and quality improvement. And he gives lots of presentations at various international conferences. He's also given courses on FPGA design and verification for both UVVM and his courses. He tries to make things as easy to understand and use as possible. Okay, and I'm going to hand over to him now. Okay, Disha.
Yes, Aspen, you're on mute.
Right. Can you hear me?
Yes, you can
Yeah,
go
we
ahead,
can.
please.
Okay, so thank you. So just before I start, I just want to briefly say that I'm from a company called MLogic. We're an independent design center for embedded systems and FPGA based in Norway, just outside Oslo. Started only 4 years ago, had a pretty extreme ramp up from 1 to 43 persons, out of which 18 are on FPGA. And we're a verification IP and methodology provider through UVVM, as Mike mentioned. We also do courses, as was also mentioned. And let's then start with requirements tracking. So what is requirements tracking? This expression is used in many different ways. And it's used everywhere, any business, any domain. I think in our domain, it could be anything like used in a complete large system consisting of multiple subsystems for embedded systems, for FPGAs, and of course going all the way down to FPGA modules as well. Requirements tracking as an expression is very often used for the system requirements hierarchy, as in mapping requirements from one level to the next level down, and then going further down to FPGA or FPGA modules. And of course, also just going from one high level down to FPGA modules directly, but then also via these levels. And also going the other way around, showing